Hi guys, so in this presentation I'll be presenting about the causes of climate change, which is 2.1 of the IB Geography syllabus, where we're going to be investigating our topics surrounding the greenhouse gases and its effects on climate change. So first of all, what is greenhouse gases? So what are greenhouse gases? They are gases that absorb long-wave radiation and they trap heat rising from the Earth's surfaces and stop it from escaping out of space. So colloquially, when we talk about greenhouse gases, we're referring to those gases that actually keep the temperature of Earth to be warm. So some examples may include carbon dioxide, methane, nitrous oxide, water vapor, and fluorinated gases. So even though this pie chart may be out of date, but you should know that carbon dioxide takes a significant portion of the world's greenhouse gas proportion. Okay, so explaining the greenhouse effect, you should first and foremost understand that the greenhouse effect is essentially a natural process. It actually keeps the average temperature of the Earth at around 15 to 16 degrees Celsius. Greenhouse gases is important for life to exist on Earth. The greenhouse effect is compared to the blanket, which traps heat, keeping the things warmer on our Earth. Without the greenhouse effect, however, the Earth will be significantly colder at around 0 degrees Celsius. So now, it has been pretty abstract, so now let's explain in detail how the natural greenhouse effect actually works. So first of all, you know the sun, right? So the sun's short-wave incoming rays, or you can refer to this as incoming radiation, whatever vocabulary you want, pass through the atmosphere. So here's our atmosphere, which we actually refer to as the troposphere, which we'll get into later. Atmosphere is the colloquial, the spoken word we use, but scientifically, geographically, we tend to use another word called the troposphere, which basically is our atmosphere layer with a distance between 0 to 10 kilometers. And then we have other layers going up and up. Okay, so when the sun's short-wave incoming rays pass through the atmosphere, the Earth's surfaces, which examples are rocks, oceans, cities, mountains, and fields, will absorb the sun's rays and warm up. So these are the short-wave radiation coming from the sun, and afterwards from the surfaces, the warm surfaces will give off energy and they will reflect these rays in the form of long-wave radiation. So short-wave in, long-wave out. That's how you memorize the essential part of this process. And then after reflection, there will be greenhouse gases here in the atmosphere, which are the carbon dioxide, methane gas, fluorocarbons, water vapor. And they're going to trap the long-wave radiation reflected from the Earth's surfaces and basically reflect them back again, while a small proportion of the long-wave radiation will escape from the atmosphere and return to the upper atmosphere, which we refer to as the stratosphere. So the heat in the atmosphere is then re-radiated back towards your surfaces. It's like a blanket, which is an analog that we use to describe what is greenhouse gas. And so now you should understand this positive relationship. When one variable increases, the other variable increases as well. Now we're referring to greenhouse gases and temperatures. When temperatures are higher, there will be more greenhouse gases in the atmosphere. So when there are more greenhouse gases, you can imagine there's like a thicker blanket. When there's a thicker blanket, it basically disables much more gases to pass through. When it is a thinner blanket, which with lesser greenhouse gases, it is much easier for this long-wave radiation to pass through the greenhouse gases and escape out into the atmosphere. So this is a way you should explain the greenhouse gas effect. It is a 5-mark question where you have to give a step-by-step explanation starting from the sun. Step 1, short-wave radiation coming from the sun reach the atmosphere by passing molecules in air. Second step is the Earth's surfaces, for example, the ocean, fields, and cities, absorb the sun's rays and reflect the waves of long-wave radiation back into our atmosphere. And then the third step, the greenhouse gases in our atmosphere trap a large proportion of this radiation and reflect them back into the space. Well, you can also say a fourth step is some of the gases will escape into the stratosphere without being trapped by greenhouse gases. So yeah, actually it's a 5-mark question, but you can talk about this in 4 or 3 steps. Okay, now 4 layers of the Earth's atmosphere, which are broken down into the troposphere, stratosphere, mesosphere, and thermosphere. So you can see this diagram shows you the variability of the height along with changes, variability of temperature along with changes and alterations in height. So when you see that in troposphere, this is where we live under, where the airplanes fly over, where we colloquially in daily English refer to as the atmosphere, although in geography, all 4 layers constitute the atmosphere because we have different names for different parts relative to different heights. So for troposphere, most weather processes take place here. You can see snows, monsoons, you can see wind, droughts, dry climates. Here you see a fall in temperature with height. So when the height increases, when we are going to visit the Himalaya mountains, when we're going to visit the Erme mountains, when we're going to, going to the Andes mountains in South America, going to the Qinghai Plateau in Tibet, China, we can see we get colder, right? We have to wear a jacket. This is because temperature, when height increases, the atmosphere stinks, meaning we are living in a colder environment. After 10 kilometers, we have a little bit of a tropopause, which is the distance between, I would say, about 25 kilometers, which is a distance, or actually about 20 kilometers distance between our troposphere and our stratosphere, where there is also an ozone layer, where you have to understand. We'll get to ozone in the next few slides. After that, it's a stratosphere that goes up to 50 kilometers. You should memorize the numbers. So troposphere is 10 kilometers. Then the stratosphere goes to 50 kilometers. And here you see there's a reverse relationship, which we refer to a positive relationship, because when height increases, the temperature increases as well. So when you go higher above in the stratosphere, which is unlikely because we humans do not really travel to the stratosphere, but then if we go, you can see that actually the temperature gets colder when the height increases. This is because the increase in temperature is due to the absorption of solar radiation. So when you go up, in this case, it's not because it's closer to the sun, but it's capable of absorbing more solar radiation. Thus, there is an increase in temperature. And some elements you can remember characteristics of a stratosphere as elect dust and water vapor. The whole atmosphere is relatively stable, relatively thin. After that, we have a stratopause. Again, difference between the two atmospheres before we reach the mesosphere, where, if you do not memorize mesosphere, how you can memorize this? Mesosphere is where there is this International Space Station, right? International Space Station actually is located in the mesosphere. So again, here you have the same thing as a troposphere. You see the relationship as temperature decreases when the height increases, and the reason is decreasing density in this case prevents the absorption of energy when height increases. So in mesosphere, as we get higher and higher, we get to a higher point. The density is going to decrease, which will act as a hindrance that hampers the absorption of solar energy. Then we have a mesopause. So mesosphere goes to about 80 kilometers. Last but not least, thermosphere goes from 90 kilometers to 500 plus kilometers. We do not know an exact number, but it goes to a pretty high point. Thermosphere is basically, I would say, analogically or scientifically, we can say it is a virtual vacuum. Vacuum is a place where there's no pressure. As you can see here, you have this pressure line. Before we even reach the stratosphere, which is our second layer, there's already no pressure, right? So same thing for thermosphere, we call it virtual vacuum because the particles do not really move. If you know chemistry, it's like imagine you are in absolute zero. Your particles are not moving. And there's a rising absorbed energy due to energized shortwave radiation. So in thermosphere, after we get to 80 kilometers in height, we see this positive relationship again when the height increases and the temperature followed by increases as well. So you have to memorize these 4 different parts ranging from troposphere to thermosphere as a 4 layer of our Earth's atmosphere. First one goes to 10 kilometers. Troposphere, stratosphere goes to 40 kilometers. Mesosphere goes to 80 kilometers. And thermosphere goes to 500 plus kilometers. Okay, and then moving on, we have to understand what is ozone. Essentially, the exam question is going to ask you, first and foremost, what is the importance of ozone? So ozone, the formula is really straightforward. Basically, it's O3. You know from chemistry, O2 is oxygen, right? CO2, you know, is carbon dioxide. Ozone is O3. It is really important to our survival, even though it's a little bit different from the gas that you breathe, which is oxygen. Oxygen is also important for you to stay alive, but ozone is also essential for us to stay alive. Why? Because it protects us from the sun's harmful ultraviolet rays and ultraviolet radiation. Imagine if there's no ozone in the stratosphere, everyone is going to get skin cancer when we are born, when we are exposed to sunlight, when we go out for a run, when we go to school, when we go down to buy some groceries in the supermarket, when we go to swing, go to play football. The sun is going to have a shield. The sun's radiation is going to highly and rapidly damage our skin, and everyone's going to get skin cancer. We are not going to survive. We are not even going to live until adulthood. We are going to die when we go out to the sun. So if there's no ozone, human civilization can't even be developed because primarily there are no buildings in this world, and if everyone dies when they're exposed to sunlight, then humans just can't survive. This species just can't survive. So ozone, O3, is just as important as O2, which is a gas we need to breathe every second, every minute, and give off carbon dioxide in order to survive. Okay, so that is first and foremost the importance of a stratospheric ozone. In the exam, this will be a 2-mark question, which will ask you to give a short explanation on the importance of ozone, and also may ask you, it could be a 2 marks or 3 marks content, asking you to give the differences between the ground level ozone, which is the ozone that exists under the atmosphere that we live, and stratospheric ozone geographically. Okay, so the stratospheric ozone is beneficial. The tropospheric ozone is harmful in many ways. Okay, so however, ozone in troposphere closer to the Earth's surface is a pollutant, meaning it's polluting our atmosphere, and it is hazardous to our health. It damages our lung tissue and causes respiratory diseases. So how is this tropospheric ozone created? It's different to stratospheric ozone, which is the first difference you can say in your exam paper. So the stratospheric ozone is created as a natural process. It's created by Mother Earth, created by Jesus Christ, if you are a Catholic. However, ozone in the troposphere is created by human beings. It's a result of human activities. So this type of ozone can be detrimental to our health. You can imagine this as our pollution. You can see in Iran, in this Iran cities called Zabul. You can see in cities like New Delhi, cities like in China as well. In many places in China, India, as well even in the UK, developed countries, South Korea, Japan, we know pollution. You can imagine ozone as essentially pollution. It is created when vehicle pollution undergoes a chemical reaction with sunlight, as vehicles produces methane gas, nitrous oxide, and remember the example I said? There's nitrous oxide as an example of greenhouse gases, and vehicle pollution basically produces nitrous oxide and carbon monoxide. And the former, nitrous oxide, is a really strong greenhouse gases in our atmosphere. Okay, so the second difference you can say that tropospheric ozone, you can say the location, it is located in our troposphere where human beings live under, and stratospheric ozone exists in the stratosphere, which is about 50 kilometers, which is about 40 kilometers up in our atmosphere. Okay, and tropospheric ozone and other pollutants also really common in urban areas, especially in late afternoons. Okay, now you understand a little bit about greenhouse gases and our layers of our Earth's atmosphere. Now we need to understand a really easy content, which is understanding the Earth's energy balance. What do I mean by understanding the Earth's energy balance? Is you have to understand that when sun gives off energy, gives off sun's radiation, incoming short-wave radiation into Earth is always going to be reflected back into the atmosphere, because in this way we are going to maintain the temperature of our Earth. Otherwise, we're only going to live in. Everyone is not going to survive. The species is not going to survive under such a high temperature. So the average temperature for planet Earth is about 15 to 16 degrees Celsius each year, taking account of the effect of greenhouse gases. So we call something called the equilibrium when the Earth will emit energy followed by sun's incident energy. So if you take physics, you should understand that incident energy refers to the energy sent by the sun emitted into our Earth, and Earth in return will reflect solar radiation energy, which is our reflected energy. So there's instant energy and reflected energy. Okay, so the Earth is approximately 150 million kilometers from the sun. Average temperature, as I mentioned, is about 15 to 16 degrees Celsius. But as we know, this topic is about climate change. We're also understanding and looking at trends, human processes, mechanisms of change, and prediction of the future. Since we're looking at these geography elements, that this average temperature has been gradually increasing. As you can see the trend, that is why we're talking about climate change. Essentially, we are focused on global warming, which means some scientists believe that our Earth's temperature is increasing by about 1 degree to 4 degrees in every 2 or 3 years, which can be a really scary trend if it continues, but it is a result that is sometimes indispensable and unescapable. Okay, what if the Earth's orbit moves closer to the sun? And I'm going to skip this slide because it basically tells you that when Earth is closer to the sun, we're going to live in a hotter environment, right? Because when we orbit closer to the sun is going to have more energy emitted into our Earth, since it will have to pass through a lesser number of clouds, a lesser number of atmospheres when they are closer. So imagine this graph right here. You have A and B. Which graph represents a higher temperature? It's graph A, right? Because there's shorter distances between the Earth and the Sun. When there's a shorter distances, the Sun's radiation, incoming short-wave radiation, will have to pass through a lower number of atmospheres before reaching Earth. So more energy is going to reach Earth compared to graph B right here. That's why we say when the Earth is orbiting closer to the Sun, our temperature is going to increase. Let's say you'll be maybe 17 to 18 degrees. Okay, now you're going to wonder, I understand the Earth is going to get hotter when we're closer to the sun, but why is it closer to the sun? So we have to understand the reason why sometimes the Earth is orbiting closer to the sun, and sometimes we get hotter temperature, and sometimes we get colder temperature. So by showing you this photo of an ice age that you may recall if you watch some movies from, is it Disney? Okay, so you see Ice Age. So now you do not see this thing often in your life. Why you don't see this often? It's not because God has turned the ice into land magically, superficially. It is because we have something called eccentricity. Eccentricity occurs over a long time horizon, over a long time cycle that is about 40,000 and 42,000 years. So we human beings live in average about 60 to 70 years. That is our life expectancy, that is our lifespan. But also, every 40,000 years, the Earth's orbit around the sun will change. Which means in every 40,000 years, the Earth is going to get closer to the sun. And after that, in another 40,000 years, it's going to orbit a little bit out, farther from the sun, right? So when you give an explanation for this, you basically have to say that the average temperature of Earth will be higher or lower when the Earth's orbit is closer to the sun. The orbit is closer to the sun for periods of time and further away from the sun at other times. So orbit is basically this circular path right here. If you know circle, it's basically a circular path right here. The Earth's orbit around the sun. So if you know mass, here's a radius here, diameter here. So when the Earth is orbiting closer to the sun, you're going to get a smaller radius. When the Earth is orbiting further from the sun, you're going to get a larger radius. So that's how it works. Okay, the Earth is tilted on its axis. The angle of tilt, you don't have to memorize this. You can see it's a little bit tilted, right? It's not exactly parallel. If you draw two lines here, the degree is approximately about 22.1 to 24.5 degrees. the Earth will wobbles back and forth on the 40,000 year cycle. Currently, this angle is about 24.44 degrees as of this slide made in 2018. This angle affects the amount of solar radiation different parts of the Earth receive. Because when it's tilted like this, you can see then this part right here will have a further distance from the sun. So whatever country is here will be colder, and whatever country is here, you can see this place where my mouse is pointed at is now a little bit closer to the sun. So the sun's radiation will have to pass through a lesser number of atmospheres, lesser number of clouds, lesser number of particles, lesser number of molecules of gas before it reaches these countries right here, which I do not know. So these places will have a higher temperature. So that is what we mean by the Earth's eccentricity. So that's why we have an ice age. Maybe 40,000 years ago, we have this situation right here. But nowadays, we do not really see an ice age with ice gradually melting. But in the future, who knows what's going to happen? Maybe 40,000 years later, we are returning to this again. But essentially, we can also result in very scary conditions like this. But moreover, is always balanced because you see there are always countries closer to the sun. There are countries located near the equator like Indonesia, Thailand, and Singapore. There are tropics countries as well, like those in Africa, like Brazil. Brazil's the Amazon River, Brazil's Amazon, this rainforest. So still, we may have droughts. We always have droughts. We always still have ice age. Also, we always have ice as well in parts of the world. But it's always based on this 40,000 year cycle that we sometimes get ice age. We sometimes get significant droughts and hot weathers. So it's always a cyclical process. It always works in cycles. Okay, so as you can see from this graph, 10,000 years to 20,000 years ago, there was an ice age because of changes to the angle of tilt. So when the angle of tilt was like this, I would say when it's orbiting closer to the sun, angle of tilt may be about 22 degrees. You can see there's this ice age where you may be familiar with. Okay, so that was eccentricity. You must memorize this because the question in the exam is going to ask you, give some reasons, natural reasons, which are not man-caused. So this reason is not man-caused reason. It's a natural reason, not caused by human activities, not caused by our economic activities and operations. And now, so that is one reason. And the second reason is global dimming. Global dimming is a reduction of sun's rays reaching the Earth's surface due to pollution. So have an understanding as this. I'll show you a volcano. So why is volcano causing global dimming? The answer is straightforward. Because when we have a volcano and the volcano erupts, it's going to add small particles into the atmosphere. So it can be rocks, it can be minerals, it can be you can be something like this, it can be different minerals. This is going to come to the space when there's volcanic eruption, significant nuclear power. It's a large amount of light energy and nuclear energy if you recall middle school science. Okay, so they are going to add small particles into the atmosphere, and as a result, what is going to happen is you'll basically block the sun's rays reaching the Earth's surfaces. That is why when there is a volcanic eruption, it seems pretty hot. It seems like it's erupting. It seems like having a fire, but it actually keeps our temperature warm, cooler at these situations because the sun's rays are unable to reach the Earth's surfaces effectively. Or you can say, simply put, there is a lesser amount of sun's rays reaching the Earth's surfaces due to pollution and eruptions. They threw millions of tons of particles of dust. Basically, you can memorize this. So dust, just like rubbish, can be some minerals, can be some basically some rocks. There's also sand, can be some ashes as well. There's small pieces of rocks. Also can be the soot. If you do not know soot is like this. It's like smoke actually. Yeah. So you have ashes, you have dust, and also you have something released from the eruptions called soot. So that is about global dimming. The second natural reason causing the Earth's energy balance to change, causing the Earth's temperature to change. And then you also have to understand the third reason, that is solar flares. It's not in the slide, but you have to understand what is solar flare. It's a third natural reason. It is basically when the sun is getting hotter. There's a sudden flash of increased brightness of the sun, observed near the surfaces, and it is a naturally occurring process explained in science. So now we have to understand tropical and polar regions. Now what I'm going to do is show you a map of the world. Okay, showing you a world map to explain whatever is tropics and poles. So now you're looking at the map. You see countries here. You see Singapore. You see Indonesia. You have Malaysia, Brunei, Timor-Leste, Papua New Guinea. These countries are located near the equator. So we call these countries tropics region nations. Okay, so we have tropics regions and regions in the poles, which are Arctic and Antarctic. So I'll show you another picture to represent what do I mean by Arctic. Show you some cute penguins. So we have this, and I'll show you Amazon rainforest. Like this is an example in Brazil. Okay. Oh, actually, equator countries. That's what I'm going to do. Whole nations. Okay. Now let's compare these two images. We have this right here. We also have this. Why do they have significantly different temperatures? You should be able to explain this, and you'll come up as a 3-mark questions. Okay. So there are two reasons for this. First of all, the countries located in the equator form approximately a 90-degree angle with the sun. So these countries right here from a 90-degree angle, so the sun's incoming rays are more concentrated. So here's the first point. When the equator is countries in the equator are perpendicular to the sun, perpendicular means for me a 90-degree angle like this, 90 degrees, and the rays are going to be more concentrated because they are going to going straight forward to the same direction. More light can reach these countries near the equator. That's why Singapore, if you look at Singapore annual climate, we'll see some data right here. You don't see snows in Singapore, don't you? You don't see snows, and from January, which is the start of the year, from Chinese New Year to December, our temperature doesn't really change, right? Our lowest temperature in average is about 25.5 degrees Celsius. Our highest temperature is stick to around 31-32 degrees. You don't see a lot of variations right here. You don't see large changes right here. You see it's always hot because Singapore is a nation located near the equator. So the first reason we're going to explain in the exam is that the equator is more perpendicular to the sun, approximately forming a 90-degree angle in between, so the sun's rays are more concentrated. Thus, there is more energy per meter square that is emitted from the sun. So in per meter square, there's more energy that is going to reach from the sun. So that is your first valid reason to explain why countries near the equator, why tropical nations receive more heat than polar regions. So here is our polar region where you've seen these cute penguins right here. First and foremost, do they form a perpendicular line? No, right? If you know math, this is more like an acute angle. I would say like 30 degrees to 45 degrees, right? Either 90 degrees, even 80 degrees. It doesn't look even 60 or 70 degrees. It seems like lesser than 50 or 40 degrees. So that's why it's less concentrated. When the light rays pass from the sun to Antarctica, for instance, or Arctic, or you can also say Russia, or cold countries right here where the winter is super cold, including the UK, you can see the light doesn't, you can see the region aren't really perpendicular to the sun. They form an acute angle in between, so there's lesser energy per meter square that is received by these regions, by these countries. Okay? So that's our first reason that you have to memorize and understand it deeply in order to apply it in the exam. And the second reason is that countries near the equator are closer to the sun. Look at this example again. Imagine there's Singapore right here. Compare these two lines, this line here and this line here. Imagine this is Antarctica. Isn't the distance between the sun and Antarctica much more larger between Singapore and the sun? Therefore, the sun's rays have to pass through more atmosphere. So here there are more atmosphere they have to pass through, and that means there are more clouds, more gases, more molecules of gases, therefore more energy from the sun when it is traveling to Antarctica will be scattered and reflected away. Maybe here, reflected here, maybe there, maybe back to the sun. So there will be less energy reaching the Earth's surfaces near the poles. Okay? So imagine here there are gases, there are more clouds, particles, gas molecules. So when the sun is working hard trying to emit its energy radiation into Antarctica, much of them can't really reach the regions eventually, whereas here it's much more easier because it has to pass through a lesser number of atmosphere before it reaches the regions near the equator. Okay, so now you should be able to understand why tropical and polar regions get different temperatures, why we have this, and why we have a desert somewhere in, like the Sahara Desert somewhere in Africa. Okay. Now you have to look at this graph here. One of the difficult part of this course is that you can see in the equator there is something called an energy surplus, and in Antarctica, all those places with 90-degree north and south, they have a deficit. Okay, so the tropics receive more heat energy, but does it mean the heat energy is always going to trap in the equator? Absolutely no. Okay, the transfer of heat goes around the globe. So in two ways, there are two ways that the heat energy in the equator, in the tropics, move and redistribute, transfer the heat into polar regions like Antarctica and Arctic. So two ways. One way is ocean currents, and one way is wind currents. Okay, so what do I mean by ocean currents? Ocean currents basically the waves, direction of the waves, or an official explanation for ocean current is, let's have a look at it. It's basically a continuous and directed movement of seawater generated by a number of forces acting upon the water, including the wind, the Coriolis effect, the breaking waves, cabling, and temperature and salinity differences. So imagine here is a polar regions. The heat is not going to be trapped here, it's going to distribute because there's wind and there's waves. If you go to the sea, you know there's wave, right? You have something like this. You have something like this. When there's a wind blowing through, there are going to be waves. And when there's a salinity differences, also the different effects that you can learn in geology, like the Coriolis effect, they will cause the currents, the water in the ocean to move. Therefore, this place right here is going to get more heat, and the equator is going to lose more heat as well. So we say the heat is transferred from the equator, where there is an energy surplus from the sun, to the polar regions, where there is originally an energy deficit. So this is the original graph, and after transfer, the line is going to look something like the green line here, and the red line represents the original situation. And the second wave is through wind currents. So wind, not only does heat reflect into the ocean, because remember our examples I've shown you, there are many surfaces with oceans, cities are also surfaces, also we have mountains, right? Rocks, mountains, vegetations, they are not in the ocean. So ocean is not the only place where the Earth's surfaces store heat. So we also have mountains, and the heat from the mountains, for example, is going to be transferred through the wind currents blowing. So every year, every season, the wind is going to blow a certain amount of heat away from the equator to the regions where there is a significantly lower amount of energy. Okay? So this is a really important example here. Okay, moving on to albedo. So you finished the most difficult part of 2.1. If you're a GCSE student in peer tutoring, you may have to understand this point as well, but it'll be more essential for IB, standard level and higher level geography students to memorize, be able to look at the graphics and be able to analyze the graphics in a straightforward and effective way. That will be the important skill that SL students and also IGCSE geography students need to be equipped. Okay, so now we finished the difficult parts. make sure you understand the graph. And okay, now moving on to albedo. Albedo is basically, simply put, whiteness or reflectivity. Albedo measures how much light is reflected from the surfaces of an object. Different surfaces have different albedos. Some surfaces have 100% of the light energy reflected, and some surfaces have 0%. Okay, we do not want to confuse you with this table here. Okay, so now I'm going to show you two things. So I'll show you one thing, this with blanky white is bleached white, where you can see here, snow, also have a dark vegetation. So if you have taken GCSE GCSE physics class or chemistry class or integrated sciences, core sciences, you should understand that dark surfaces absorb more of the sunlight, and white surfaces, on the other hand, reflect most of the sunlight and absorb only a small amount of sunlight. Okay, so the snow has a very high albedo. Why does it have a high albedo? Because it reflects much of the sunlight back into the atmosphere, where only a small amount of sunlight will be trapped here on the snow. On the other hand, you have dark vegetation here. They have a low albedo because albedo, remember, it is how reflective is the object. It measures the whiteness or reflectivity of an object, and this dark vegetation trap a significant, I would say maybe 70 to 80% of the heat coming from the sun and reflect a smaller proportion of the sun's energy back into the atmosphere compared to the snow. We say the dark vegetation has a low albedo. Okay, so if a surface has a high albedo, more of the sun's shortwave energy is reflected directly out into space. Fresh snow has a high albedo. Dark surfaces, another example here is the tarmac road, which you can see. That's why the road is really hot, right? The tarmac road also has a really low albedo. It absorbs about 90% of the sun's energy and only reflect 10% of the sun's energy back into the atmosphere. So here, after you understand albedo, you can have a look at this table right here. Snow, as I mentioned, old snow has a high albedo. Dry sand, grass, they have a low albedo, and lowest albedo here exists between the dark white soil and black rose surfaces, as well as water. Because of water. Water is more of a different example because it's neither black or white. It's hard to say whether it is a measure of whiteness or darkness because water is essentially transparent. So make sure you understand this outlier here. The water also has a low albedo, even though it doesn't fit into our original definition. But in the test, if you mention whiteness or reflectivity, you should be able to get a mark. And it always comes out at a 2-mark question when the examiner wants to ask you to explain the albedo effect and why do certain objects have a low albedo and what does it mean to your atmosphere. Okay, so when an object has a low albedo, it means it basically absorb a large amount of sunlight, and that will keep our temperature hot, like the tarmac road or the dark vegetation. And we have ice. When we talk about ice melting, when we talk about the snow, they have a high albedo, reflecting a large proportion of light into the atmosphere, therefore keeping our temperature cool or maintained at a level that is not going to be warmer. Okay, so before moving on to enhanced greenhouse effect to finish our unit, we are going to be talking about positive feedback loop, which is link to our albedo. Okay, so what do I mean by a feedback loop? A feedback loop is when a reaction causes the number of reactions to increase, when the product of a reaction causes the reaction to continue. So that is what we mean by a positive feedback loop. Okay, so changing albedo is one of the feedback loops you have to remember, especially for IB geography students. There are two types of feedback loops that we're going to go through. The first type is the soil in tundra, and the second type, we're going to talk about albedo first. The first type is going to be albedo. Second type is going to be soil in tundra. This is two examples we have to understand in terms of our feedback loop. So when ice melts, the first process starts with ice. When the ice melts, you'll expose more of a dark vegetation in Earth's surfaces. So imagine there's not a layer of ice. Okay, so that's going to cause more vegetation and rocks to be visible and more dark surfaces to be exposed to the sunlight and the atmosphere. On the global level, the Earth will lose its ice, so the albedo for the planet will fall. What do I mean by that is, imagine when ice melts, you have a dark vegetation, you have the rocks, you have the, all the particles, the dust, which are exposed to the sunlight. They are going to absorb much more sunlight because they have a low albedo, which I went through in the last slide. By having the low albedo, they are going to receive and trap much more of the sunlight into our Earth's surfaces rather than reflecting them back into the atmosphere. And this will cause the temperature to increase, and this will then cause more ice to melt. More ice to melt causes more vegetation to be exposed, which causes Earth's albedo to be lower again. Lower albedo means the temperature will be higher, even more higher, and causes more ice to melt. So hope you can get the idea of how the positive loop works in terms of albedo when we link to ice, link to these white surfaces, when ice melts, when ice age finishes, when ice age ends, to a continuous increasing temperature. So what you should take away from this feedback loop is, when the temperature increases, it will forever increases. That's why we are worried about global warming as a potential scary and potential threatening effect in the world of geography. So that was the first positive loop. And the second feedback loop is about the tundra. It's about the releasing methane gas. So methane gas, I went through during the introduction of the video, is an example of greenhouse gas, right? So the thawing, this word basically means melting. So when you go to the kitchen and take out your yogurt, take out your meat for today's dinner, you are thawing the meat, right? Thawing basically means cooling down, warming something from the fridge or something like that. Okay, so here, tundra is also known as a permafrost. It's a piece of land where there is a layer of permanently frozen soil, right? Basically, you can memorize tundra as permanently frozen soil, because water in the soil is frozen all year round, so it's always frozen. It's like a solid, even though it can be turned into a liquid, can be turned into a gas. Inside there are gases. The frozen soil is like a cap on the bottle, doesn't allow the gas to pass through. So normally, when there's a cold temperature, the methane gas is just going to be trapped inside underground. It's going to be trapped underground, and the whole tundra or the permafrost is going to be frozen because the soil is frozen, and that is then because the water in the soil is frozen all year round. However, when the temperature increases, it does not allow gas to pass through because the methane gas is created by rotting vegetation. So what happens is, imagine the temperature now increases. Imagine the temperature now is increasing. Imagine the temperature now is increasing. Now, what happening is, the tundra is not frozen anymore. We are not calling this as a permafrost. Now the soil is not going to be frozen. It is going to be a liquid, right? And the effect of it is the gas is going to pass through. And the methane gas is going to release. There's not going to be a cap on the bottle. The methane gas is going to release underneath the tundra and safely stored. It is a powerful greenhouse gas, which is a fact you can memorize for a marks question or for potentially an essay question, that the methane gas is about 32 times more effective at trapping long-wave radiation than carbon dioxide. Okay, so as the Earth warms, the more tundra is going to melt. More tundra melting means more methane gas is going to release into the atmosphere. More methane gases into the atmosphere, which is a greenhouse gases, right? When there's more methane gases in our atmosphere, remember, going back to our first and foremost slide where we talk about greenhouse gases here, the greenhouse gases are going to trap the long-wave radiation, right? So when there's more methane gas, meaning there are more greenhouse gases, then it's going to trap more long-wave radiation reflected from the Earth's surfaces coming from the sun and keeping the temperature warmer. When the temperature is warmer, be careful, when the temperature is warmer, we're going to have more tundra melting, so it's going to get the feedback loop again. And it's a positive feedback loop because when temperature increases, it's going to increase more. Okay, so this is also the difficult part of GCSE climate change geography chapter, where you have to memorize the two positive feedback loop. So giving a recall, so the first feedback loop that we've been talking about is about change in albedo. When the temperature increases, more ice is going to melt. When more ice is going to melt, the darker surfaces is going to be exposed to the atmosphere. For example, vegetation, dark vegetation, the rocks, and they have a low albedo because they are darker in nature, they are darker in color, meaning they are going to trap a larger amount of heat from the sun and reflecting a smaller amount, unlike the ice. They have a low albedo, then the temperature causing the temperature to increase. the increase in temperature is then going to cause more of this darker surface, more ice to melt, and more of this vegetation and rocks to be exposed. And then the temperature is going to increase again. So on and so forth in a cycle. Okay? So the thawing tundra is more easier to understand, I believe, than the first positive feedback loop. What happens is you in the exam, it should be a 4-mark question or a 3-mark question. You first give a definition to the examiner about what is tundra. So you can basically memorize this definition. Here it is a piece of land where there is a layer of permanently frozen soil because water in the soil is frozen all year round. And the methane gases is trapped inside the tundra and it does not escape into the atmosphere because it's frozen. The whole tundra is frozen. It's like a cap on the bottle. However, when temperature increases, more methane gases is going to escape from the frozen soil, causing more greenhouse gases to occur, causing the production of more greenhouse gases into the atmosphere. And the consequence of more greenhouse gases is a higher temperature, and higher temperatures is then going to cause more tundra to melt, forming a positive feedback loop. So that is how it works. And now following the feedback loop, we have to get to the negative feedback loop, where we're going to be talking about the reverse effect. So we've been talking about how increase in temperature is going to cause an increase in temperature. Now we're going to be talking about how increase in temperature is going to cause a decrease in temperature. First and foremost is increase in evaporation. When temperature rises, there will be more evaporation for oceans and other water sources like lakes, canals, like reservoirs. This will going to create more cloud cover and more of the sun's rays are going to reflect it back into space. You know, chemistry will have evaporation, turning from liquid to gas, like boiling. An increase in the Earth's albedo will then limit the rise in temperature. So how do you memorize this? Is you memorize that there's when temperature increases, there will be more evaporation, more liquids are going to turn to gas. This will basically cover sun's rays and basically form more cloud cover. They will reflect the sun's rays and reflect them back into the space. The second way to explain the second negative feedback loop is increase of vegetation growth. How do you explain this increasing vegetation growth? Is that as more carbon dioxide gases is released through burning fossil fuels or higher temperatures, there will be higher CO2 levels. Higher CO2 levels will increase the rate of photosynthesis in plants and trees. And then the vegetation grows, vegetation is going to grow at a faster rate. You know, if you know photosynthesis, if you let's revise the formula of photosynthesis in case you forget. But I think it's been went through in middle school science. So photosynthesis basically is an equation that when carbon dioxide plus water is going to equal to glucose and oxygen gas. So let's have a look at the carbon dioxide equation. So now we have carbon dioxide and water. So when plants receive more carbon dioxide, it's going to turn into glucose first and foremost, which is the food the plants make. It's a type of sugar the plants have to eat. It's like a starch. And they also produces oxygen and water. That's why trees are important for us. We human beings have to breathe. So when the higher CO2 levels, it's going to increase the rate of photosynthesis. Rate basically refers to speed, meaning more plants are going to produce oxygen based on the carbon dioxide absorbed. And as a consequence, more vegetation is going to grow at a faster rate because glucose is basically the food of plants. Like humans have to eat hamburgers and humans have to eat rice or noodles, plants have to have glucose. So the extra vegetation will absorb more carbon in the atmosphere when vegetation grows at a faster rate, and this will indeed reduce the amount of carbon dioxide gases and reduce the global temperature. Okay, so you finish the harder parts, 2 positive feedback loops and 1 negative feedback loop. And now I want to go back to one of the easy topics of climate change, especially for GCSE geography students. It's about carbon stores before industrialization and after industrialization. So you do not have to worry about this graph here, but a common 2-mark question is to ask you, how are carbon stores today different from maybe 100 years ago, maybe 200 years ago, maybe 300 years ago? You give the same answers. So before the industrialization, I show you an infographic representing what is industrialization. Before industrialization, the carbon is stored before industrialization, before this factory work, massive and heavy manufacturing production process have been going on, the carbon was mainly stored in forest vegetation and fossil fuels. So fossil fuels are basically these underground deposits like natural gases, coals, this coals, coals and natural gases, where you know from your middle school sciences and humanities, and you also have forest and vegetation. That was 100 years ago, before industrialization, before Britain was manufacturing this, using the machineries to carry out manufacturing work. After industrialization, around the 1900s, and today, mostly we have lesser carbon stored in our vegetation and fossil fuels, and we have more stored in atmosphere and oceans. The reason is we are burning more fossil fuels for production, to power off the machineries, for our mobile phone use, to power off our economy. When we need more electricity, when we need more electrical energy, we burn more fossil fuels, which are the non-renewable energy sources. Therefore, more of the carbon is going to be released and be seen in the atmosphere. Also, the ocean as well, as a consequence, followed by this first fact right here. When there's higher concentration of carbon in the atmosphere, the oceans are going to absorb a significant amount of it. That's why now, post-industrialization-wise, we have more carbon stored in our atmosphere and the ocean, whereas pre-industrialization-wise, more carbon was stored in vegetation and underground. Okay, so this is pretty much about this topic here. And last but not least, we're going to be looking at the human geography part of this by understanding the greenhouse gas emissions between different nations. Okay. So have a look at this graph. You can see China. This is the top 10 to 20 countries producing large amount of greenhouse gases. So you can see there's China, USA, India, Russia, Japan, Germany, South Korea, Canada, Brazil, Indonesia, Saudi Arabia, United Kingdom, Mexico, Iran, and Australia. So greenhouse gases emissions are uneven. Some countries produce much more greenhouse gases, whereas some countries produce much less. So, you can see China is in the lead, but in the exam, the question is going to ask you, if they ask you to make an analysis, write an essay, or make a 5-mark question asking you to make an analysis on international variations in greenhouse gas emissions, you should be looking at this column right here, which is a much fairer analysis in my perspective, because we are talking about per person, so we are talking about greenhouse gas emissions per capita. Okay, so now if you look at per capita, what's in the lead is going to be Australia, Australia, Saudi Arabia, and Canada, USA, whereas China is now not in the lead. But China has a largest total amount of greenhouse gas emissions, as China is a country with a high population. So before I end this video, I'll be sharing you some reasons why greenhouse gas per capita is higher in some countries and lower in some other countries. Let's look at these examples here. Okay, it's not here. I'll just verbally talk to you. So, okay, the first reason that we are concerned about. We want to concern about per capita greenhouse gas emission is wealth. Okay, so many factors are linked to wealth. Even though poorer countries, some countries which are heavy in manufacturing, heavy in the secondary industry, they may produce higher greenhouse gases, even though people are poorer in average because they rely on production. Whereas the richer countries like Germany, Switzerland, and Norway, they rely their economy on their tertiary sector by providing services. But however, electricity use is linked to wealth. People in richer countries use more electricity, right? So they are maybe social. Imagine like an example is Instagram, 3 hours a day. If you use a lot of Instagram, you're using much more electricity. More electricity means more burning of fossil fuels, right? Equal to more greenhouse gas emissions. And another example is meat consumption. When people eat more meat, what happens is animals produce waste. And animals waste produce basically methane gas. And methane gas is a greenhouse gas, a strong greenhouse gas. And if we consume more meat, or let's say this, we're richer, more meat, and then it means we need to breed more animals, boost animal reproduction, right? We want more animals to reproduce, so we have more meat to sell. There's a market demand right here, supply and demand. That means more greenhouse gases then, right? And the next one can be traveling. Richer people do travel more. So for instance, just now we see Australia has a high greenhouse gas emission per capita, and we see China, despite having a high total greenhouse gas emission, has a relatively low greenhouse gas emission per capita compared to the other more developed nations on the list, right? Isn't it a fact, right? So traveling, richer people, when we're richer, more trips, right? You may go to Europe from US, go to Asia, go to Japan, Singapore, go to UK, US. More trips, more airplane flights. More airplane flights means more nitrous oxide released because of fuel used. Same works for trains, MRT, subways, vehicles, blah blah blah. They also have more. If you have more trips, you go to more nitrous oxide, which is a very strong greenhouse gases. Plus, also they release carbon monoxide. But carbon monoxide is a weak greenhouse gas. Its formula is CO, unless CO2 is carbon dioxide. And the last reason is the size of area of houses. Areas of houses is the next reason. For instance, let's compare US with China. US is more developed, first of all, versus developed, more developed in terms of economy. US also has a smaller population density compared to China. So in USA, people live in large houses, right? Like 3-level villa with a car park, with stuff like that. When there's large amount of houses, there'll be more large amount of housing means, okay, larger houses equal to more electricity use, isn't it? More lights, more electricity. Even though you may not use the light, there's some waste. More electricity use means more burning of fossil fuels. More burning of fossil fuels means more greenhouse gases. Some examples we can give also includes nitrous oxide, carbon dioxide, and can be methane gas as well. Methane gas, or you can say fluorocarbons or fluorinated gases. Okay, so here are some examples why we see Australia, even though China and in the lead, Saudi Arabia in the lead, we see these rich countries have a high per capita emission. Some reasons can be this, well, there can be many other factors. Okay, so that's pretty much about this video here. So we went through 2.1, the causes of climate change, the hardest unit in chapter 2. And have any questions, please comment below. Thank you.